In my previous presentation titled Thermodynamic Non-Idealities in CO2 Capture with CAF20 Part 1, I had highlighted the thermodynamic non-idealities for CO2 water mixture adsorption in CAF20. I had identified two different scenarios that manifest at low values of relative humidity and high values of relative humidity. At low values of relative humidity, the adsorb phase is significantly richer in CO2, i.e. poorer in water than anticipated by the IAST. On the other hand, for high values of relative humidity, the adsorb phase is significantly poorer in CO2, i.e. richer in water than anticipated by the IAST. I had also stressed the fact that the mixture adsorption data on which the analysis is based is obtained from breakthrough experiments that are not conducted under strict thermodynamic equilibrium conditions, and that explains why the water loadings at high relative humidities exceed that from the as compared to the unary water loadings. Such phenomena are not easily captured by mixture adsorption theories. My aim today is to consider the modeling of the mixture adsorption phenomena using the real adsorped solution theory, so that the RAST could be used in process design of CO2 capture in PSA technologies. The material I will present today is entirely based on my article co-authored with Jasper van Barton, published in Separation and Purification Technology, that is available online, and this is the digital object identifier. So let's look at the theory of the real adsorbed solution theory. In the RAST development, we introduce activity coefficients when relating the partial fugacities of each of the components in the bulk fluid mixture with the corresponding mole fractions x sub I in the adsorbed phase mixture. This term here, P sub I superscript 0, is the sorption pressure of species I. The sorption pressures of species I are such that the spreading pressure for mixture adsorption equals the spreading pressure of pure component 1 equals that of pure component 2. The spreading pressure is pi. A is the surface area per kilogram of the metal organic framework. R is the gas constant, T is the temperature. Since the surface areas are not easily accessible from experiments, it is convenient to define a surface potential phi, which is the product of the spreading pressure times the specific area divided by RT. This can be determined from the equations given here. For further details, I refer you to previous video presentations on the Ideal Adsorbed Solution Theory. So the absorption pressures and the surface potentials can be derived from data on the adsorbed phase mole fractions and partial fugacities in the bulk gas phase mixture. In bulk fluid mixtures, the activity coefficients depend on the mixture compositions, say mole fractions xi. The situation is different for activity coefficients in the adsorbed phase within microporous materials. In this case, the activity coefficients of any component I depend not only on the adsorbed phase mole fraction xi, but also on the pore occupancy. We must satisfy two sets of limiting conditions. As the adsorbed phase mole fractions of any component I tends to unity, the activity coefficient of that component must tend to unity. Additionally, if the pore occupancy theta, which is related to the surface potential phi by this expression where Q sat mixture is the saturation capacity of the mixture, this expression for the pore occupancy, as this tends to 0, the activity coefficients for all guest molecules must tend to unity. In order to establish how the RAST models should be developed to quantify CO2 water mixture adsorption and CAF20, we resort to configurational-bias Monte Carlo simulations of mixture adsorption. Two types of simulations were conducted as detailed in my paper in separation and purification technology. On the left-hand side, we have one set of CBMC simulations in which the total fugacity of the mixture is maintained at 15 kilopascals and 298 Kelvin, and the mole fraction of water in the bulk fluid phase is varied, and this implies that the percentage relative humidity is varied. And the CBMC data are shown for water by the blue triangles, and the red circles are for CO2. In a different set of CBMC simulations, the bulk fluid phase mixture is at a constant composition of 95% CO2 and 5% water, and the total fugacity in the bulk phase mixture is varied from the Henry regime to values approaching pore saturation. From the CBMC data, the activity coefficients in the adsorbed phase mixture can be backed out, as explained in this article of mine. And for the two sets of CBMC simulations, the adsorbed phase activity coefficients are shown in this diagram on the left for this CBMC data set. where the activity coefficients are plotted as a function of mole fraction of CO2 in the adsorbed phase. In this case, for the CBMC simulations on the right hand side with constant bulk gas phase composition corresponding to 5% water, the adsorbed phase activity coefficients are plotted as a function of the surface potential that serves as a proxy for the spreading pressure. The two sets of data on the activity coefficients provide essential clues on how to set up the RAST model for the activity coefficients. We note that there are certain limiting values to be respected. When the mole fraction of CO2 in the adsorbed phase approaches unity, the activity coefficient should also approach unity. This also holds for water. When the mole fraction of water in the adsorbed phase is unity, the activity coefficient of water in the adsorbed phase is unity. So this is a constraint that must be observed by models for the activity coefficients. In addition, we need also to respect the fact that in the Henry regime of mixture adsorption that corresponds to values of the surface potential approaching zero, both activity coefficients should tend to unity. In other words, the activity coefficient models should not only respect the limiting values for the activity coefficients with at either ends of the adsorbed phase mixture compositions, but also they should respect the fact that at low pore occupancies in the Henry regime, both activity coefficients should tend to unity. In order to satisfy the limiting conditions discussed in the foregoing slide, we must use models to describe the activity coefficients that allow the proper limiting behaviors to be reflected for mixture adsorption in microporous crystalline materials such as metal organic frameworks and zeolites. The models for the activity coefficients must include a correction factor that is shown here, which is 1 minus exponential of a constant value C times the surface potential phi. This factor is representative of the pore occupancies. When the pore occupancy is 0, the activity coefficient should tend to unity, and the introduction of this correction factor ensures this. So when phi tends to 0, 1 minus exponential of minus C times phi, which is this correction factor, tends to 0, and therefore gamma I tends to 1. So the introduction of such correction factors is of vital importance in setting up the proper RAST models to describe the variation of activity coefficients in the adsorb phase mixture. It is to be noted that in the Carr-Marshall paper referenced here, the correction factors have been ignored, and this will cause the RAST model to incorrectly represent the variations of the activity coefficients with varying surface potentials. Further details are provided in my paper in separation and purification technology.